Okay, so hello everyone. We're going to continue with refraction, and let's talk about some conceptual examples. Some things that we see around us in nature that involves refraction. So dispersion. Now you know what visible spectrum is. When you uh, align all the radiation frequencies according to the electromagnetic radiation according to their wavelength or according to their frequency, we call it, that whole list of different waves, we call it the spectrum. Now here we are looking at just the visible part of that spectrum. So you see that in the order of increasing wavelengths from left to right, shortest wavelength, ultraviolet, the bluish color light, and with increasing wavelength it goes towards green, yellow and red, and then comes to infrared. On the other hand, if you go when you're going from left to right, it's the frequency decreasing. Alright, so this is just a chart of the visible spectrum part. Now what is dispersion? Index of refraction of many transparent materials such as glass and water varies slightly with wavelength. Now when we talk about bending of light, we mostly talk about the white light. It's the combination of all the visible light together. Now if we have like a beam of light coming in, imagine like a flashlight, light beam comes in and it bends as a total, the whole thing, all those wavelengths inside that beam, they bend, everything bends together. But if you look into the fine details, the different wavelengths inside bends slightly differently. So this amount of bending within a particular medium, it depends on the refractive index of the medium, plus it slightly depends on the wavelength as well. And that's why using a prism, you can separate visible light into its colors. Right, white light comes in. If you see in this diagram, it bends twice in this case. So here we have the prism. White light comes in. Over here, you draw a perpendicular to the surface of the glass. It bends. Now if you draw it as a whole, it bends like this. Right? Here's a big angle, here's the small angle. And then it strikes this second medium. This becomes the incident angle for the second surface, second refraction. And it again bends away from it, right? It's away from it, making a bigger angle. But if you look into the fine details, this bending actually splits the beam into its constituents, right? Its parts. So over here you see that it bends first into red, orange, yellow and all that, and then it bends again. So you can see different colors of the incoming light. Alright, so this is called dispersion of light, separation into different wavelengths. This is how prisms and water droplets create rainbows from the sunlight. Next example, you can see that. So what's going on here? Sunlight comes in. Now here we have water droplets. So how do we see the rainbow again? So you have to have sun. You have to have some kind of rain cloud. You have to have rain. And you have to be over here. The person has to be between, the sun needs to be behind you, the rain should be in front of you. So if you think about a rain droplet, light comes in. Let me redraw this. Light comes in. Here, like a prism, like this water droplet comes in. You draw a perpendicular, it bends, right? It bends, and it separates the light. It separates it into different colors. And over here, at each of these colors will have their own perpendicular lines, but this time, while some of the light getting out, some of the light can reflect as well. Now these different colors are reflecting back, and it comes to you, the person is here, so it bends and then reflects and then bends again, but comes to your eyes. So as a result, you see these different colors, the rainbow. Something to think about. Why is this thing half a circle? Why it's circular in the first place? Why not like a straight line or a triangle or something? Why does it look like a narrow band, like a half a circle? Why half a circle? Why not a full circle? Do you ever get to see a rainbow as a full circle? So something to think about, right? Your self-study. Okay? All right. Moving on. So let's look into refraction, another application or another different example of refraction. Going back to the ray diagram, we know that if it is going from a thinner medium to a denser medium, air to water, for an example, here's the perpendicular line, incident light, refracted light. If I increase the angle, or if I increase this theta I or theta 1 like this, now I have a bigger angle, this is going to get increased, right? Initially it was this, now it's bigger. If I increase it further, I'm increasing the incident angle, make it bigger and bigger. This refracted angle also getting bigger. Okay. Now let's look at the opposite of this. You are shining the light from underwater. So here's the surface, air, water. Let's draw a normal. Let me use some different colors. Alright, let's use this color. Here we have a theta I, and here's the respective theta R. I'm going to increase the angle. Here we have theta I. Refracted also getting bigger. No, I want to make it a little more bigger. Gets bigger, right? So I'm going to keep increasing this, and at some point theta I, the light will get so big, refracted angle will get so big, it's gonna just go over the surface of the water, making theta R equals to 90 degrees, right? It's perpendicular over here. It goes over the surface. So this dotted line is perpendicular to that. So your theta R becomes 90 degrees. At this point, we give this a new name. This theta I, we call it theta C, the critical angle. Critical angle. This is the incident angle when light goes over the surface. The refracted light travels over the surface of the boundary, right? At that point, the incident angle, we name it as critical angle. Now, what if I increase this further, right? So let me redraw the diagram with just the critical angle. So here comes light coming in with theta C, and should I use a different color? Hold on. never mind. Nope, it's not the right color. Sorry about that. Come on, color change. Okay. Coming in with theta c, refracted light goes along the surface, making 90 degrees over here. This is the critical angle. If I go beyond little bit, so I forgot to tell you. Alright, so here, going back to the first diagram, for all of these refractions, there's a little bit of a reflection as well, starting from the blue light. While it's refracting, some amount reflecting with the same angle. While it's refracting, some amount reflecting. The red one also. So there's a little bit of a reflection. Okay. So these are all reflected light. This is the refracted. So same thing here. While it's refracting, little bit of light, little bit. So I'm going to draw a thick line over here to indicate that. And some amount refracts, little bit reflects, making the same angle. Now if I go beyond this, right, if I increase the incident angle more than theta c, let's use this color. At this point, when you go above the critical angle, nothing refracts, everything reflects. Everything reflects. This situation is called total internal reflection. Now this is a pure reflection. There's nothing refracts, nothing goes to the other side, everything reflects. When incident angle is bigger than theta c, when theta I bigger than theta c, total internal reflection occurs. Alright, everything reflects. Okay. So the slide to this on the right also shows the total internal reflection. Here for small angles you have reflection and refraction, but here at point I and J we are increasing the angle. So you can change the incident angle by moving the source, or you can change it by looking at it from different points, right? So when you go further away from that point K, light goes along the surface. Now we have reached critical angle theta c at point K. Little further, when the angle gets little bigger than theta c, everything reflects. Remember, this happens only when light goes from a denser medium to a thinner medium, right? Because when it goes from denser to thinner, you are making a bigger refracted angles. It doesn't happen the other way. If you go to this first diagram over here, number 1, for any light that is coming in, there is a refracted light because the angle is smaller, right? So even if you have something coming along the surface, it still refracts like this. So it doesn't make sense to talk about total internal reflection if light goes from thinner to denser. It always should be from denser to thinner. Here's another thing. So the person underwater is looking up and get a much larger view of the surroundings, right? Because light from many areas around the person can come to the person because of this internal bending. Okay. Alright, so let's see what happens to the Snell's equation in this case. I'm going to clear this. I'm going to draw a diagram. Let's see what color. Okay, I need to change the color to Okay, let's look at this total internal reflection one more time. Let's say this is air with and water. This is N1 incident, first medium. This is N2. Here comes light. Let's say we are at theta, okay, before theta 1 and theta 2, right? This is some reflection. We haven't reached the critical angle yet. So we can write N1 sine theta 1 equals N2 sine theta 2. Now, we're going to increase this. Okay, second diagram. We're going to increase this to theta c. At that point, we know the light going to travel along the boundary, along the surface, making theta 2 90 degrees. Now, theta 1 is theta c. So, we can write N1 sine theta c equals N2 sine theta 2, which is 90. N1, which is water, right? This is water, so that's, well, let's leave it as N1. N1 sine theta c equals N2 sine 90 is just 1. This gives you sine theta c equals N2 over N1. Here's a way to find the critical angle between two mediums. We can't say critical angle for water or critical angle for glass. You don't define it like that. It's always critical angle from water to air, critical angle from glass to air, from one medium to another, and it comes from the division of the ratio of the two indices, right? So best way to approach this is, remember this, how to set up this equation, and then you can come to this. So for an example, what is the critical angle? What is theta c from water to air? We'll start here. N1 sine theta c equals N2 sine 90. N1, which is water, first medium, 1.33 sine theta c. N2, which is air, let's take it as 1 sine 90, it's also 1. So we have sine theta c equals 1 over 1.33. So what is theta c? Let's do the math and find that out. 1 divided by 1.33 equals this. Shift sine 48.75. Water to air. If this angle is bigger than 48, when it becomes 49 degrees, next instant it's gonna reflect completely. That is total internal reflection. Okay. All right. Total internal reflection has nice applications. Let's go over a few. Can read what it says. Total internal, this gives true 100% reflection, which even the best mirror cannot do. A mirror does not do a complete reflection. If you think about a mirror, it has a glass surface and some backing. Light comes in, reflects, and some of it goes in, reflects again, comes out, something like this. there could be little bit of light get absorbed by the this reflective surface. But when it comes to total internal reflection, 100% reflection, right? Here, if you look at this arrangement, there's a prism. Light comes in. Over here, the light does not bend because it's hitting perpendicular to that, comes in on this surface. Here's the first surface it strikes with an angle. So if this angle over here, if it is bigger than the critical angle of glass to air, it is bigger than that, it's going to reflect. So they make these arrangements in such a way that it strikes the next surface. Over here, this is the incident angle. If this is bigger than, again, glass to air, it's going to reflect like this, and it will come out. Now, why do we need these kind of things in binoculars? Now, we can have just two lenses. We'll come to this in the next chapter. We can have two lenses and do the magnification, but there has to be some particular distance between them. These distances can be in the order of maybe a meter or so, maybe more than that. So binoculars, if it is too big, it's difficult to handle, right? These are for field experiments kind of things, bird viewing. So you need to make the distance between them shorter. So by using two prisms in this arrangement, you can actually have light traverse that required distance, but bring them much closer. Okay, all right. I mean, you can do the same thing with two mirrors. So here's the eyepiece, light comes in, you have one mirror over here, reflected this way, you have another mirror over here, reflected this way, another mirror goes up here, goes up here, and another mirror, and then goes to the lens, and can do all the optical stuff we need to do with the lens. But mirror is going to take off some of the light, right? So it's going to decrease the strength of the light. So a good quality binoculars will have nice prisms inside. Optical fibers also depend on total internal reflection. They are therefore able to transmit light signal with very small losses. So here's the optical fiber magnified view. This is glass outside, could be air or something else. So light comes in, and because these things are so thin, no matter which angle it enters, so here comes a light beam, no matter which angle it enters, it always bigger than glass to air critical angle, so it reflects, and it again creating a big angle, so it reflects again. So likewise with consecutive reflections, the light can travel through the optical fiber. Advantage, it doesn't need to be a straight line. You can have the light going through a bend like this, through multiple reflections, right? That's one thing. And using this technology, you can use light in order to for communication purposes. Usually we have electrical signals. So if you have like an electrical wire carrying some signal, you have to think about the resistance and all that, and it won't travel that fast. The signals have something called the drift velocity and all that. Mostly there's losses. But when it comes to light, it's much faster. It's almost the speed of light, right? It's little slower than that because it's going through glass, but still it's really fast. and the losses are really small. There's no resistance, heat losses or anything. So that's why optical fibers are used in high-end communication, and this is what it is, total internal reflection. Okay, so with that we come to the end of this discussion. All right, thanks.